We will extend this basic discussion we are having, looking again at the figure we saw already in chapter 7 and in chapter 8 already. Once the surface levels, sea level pressure, low in the tropics, subtropical highs, subpolar lows, corresponding almost geostrophic looking winds. You take your flow, add Coriolis, you should get easterlies here. There is a minimum on the equator, or near the equator, corresponding to the intertropical convergence zone, where winds, meridional winds, will go to zero and all the winds will get to, so here you see meridional winds and all the winds will get weaker, and we have strong westerlies. We will repeat these, but then we will say actually in reality there are no steady westerlies. It'll be all just eddies. Right? So there was the convergence in the meridional winds. In equilibrium, the net frictional drag on the atmosphere has to be zero, as I said before. The torque cannot be positive or negative, because then the Earth will wobble as it goes along. Okay, so the easterlies provide a torque and the westerlies provide an opposing torque, and there is a balance. The length of day does change a little bit, by a few microseconds, and as I said, El Nino changes it by a few milliseconds as well. There are also atmospheric tides which do that as well. Okay, so putting it all together, then we have an axisymmetric solution. What we have done here is, even though we looked at a little bit more complication than just the zonal mean meridional, we still haven't added the asymmetry across the equator of land distribution, ocean distribution, and so on. So we will see that this flow is not as symmetric as it appears here, but we already saw that when we looked at the zonal mean meridional winds. We said the whole system moves back and forth with the sun, and also that the ITCZ is not symmetrical and the radiation balance is not symmetrical, and so on and so forth. So nonetheless, again looking at the zonal section, the Hadley cell now with the easterlies, basically it's northeasterlies and southeasterlies converging into the ITCZ, ITCZ, with rising motion. In the ITCZ, obviously there's a lot of rain, hitting the ceiling at the tropopause, going off, having the subtropical jets, and sinking over the subtropical highs, right? So you're bringing westerly momentum down, and throughout the middle of the Hadley cell, you have what are called trade inversions, okay? Maybe I'll show a figure later on. I think I already probably showed it once. There is a nice figure from NCAR, their COMET program, which shows these trade inversions, which means the rising motion is not strictly confined to the ITCZ. That's where it's very concentrated, and that's where all the rain happens. But as you go off towards this subsidence, there is a little rising and sinking motions. Everything is kind of unsteady, let's say. Okay, so you have this trade inversion happening, strongest being in the core of the subtropical highs. So this is just confirming again what we saw before, that the temperature gradients here are basically flattened out because of the energy transport associated with this divergence from the ITCZ. So energy is being transported, and the thermal gradients are being wiped out. Okay, lifting energy from here as evaporation and condensing, moving energy poleward. We will come back to this, but you will see that strangely air is coming from warmer, from colder temperatures into warmer tropics. So how is the energy transport being done? It's not just thermal energy, obviously, because thermal gradient is very weak here, and air is going from colder temperatures to warmer temperatures. So obviously we will need something else, and we'll see what it is. So you can also see the weak meridional temperatures in the meridional heat transport as seen by the potential temperatures, which obviously look very different than the in situ temperatures, right? So you have rising isopotential temperatures, or isentropes as we call them. You also remember the potential temperature lapse rate is stable to dry convection. Then we need moist potential temperature for convection. So the moist potential temperature is also different because it basically convection basically makes the moist potential temperature fairly uniform in the convecting regions. These slopes are important. We will see later on that if you move a parcel of warm air towards the poles, you are going to go up towards colder potential or colder temperatures. So how the energy is moved will depend on how you move in these kind of constructs. Okay, so you can see that if you just move along these lines, you probably don't move energy, so you will need something special. Plus there is what we would call locked up potential energy here, because you have warm potential temperatures potential temperatures being low here and increasing towards the latitudes, higher latitudes, whereas you have these horizontal gradients, right? Which means you are holding air parcels up, and you have locked up the potential energy with them. If you displace them, you can release that potential energy into kinetic energy, which is our winds. But how do we release it? That's the key question for general circulation. I'm just introducing these concepts, but we'll look at them again and you'll see what I mean. Okay, so just remember the potential temperature profiles, and we will use them again when we want to consider available potential energy and conversion to kinetic energy.